Welcome to our lecture on pressure systems and wind systems. Today, we are going to dive deep into the invisible forces that shape our weather, starting with atmospheric pressure and the various factors that dictate how and why the wind blows.
Let's start with the basics. What exactly is atmospheric pressure? Imagine a column of air extending from the surface of the ocean all the way up to the edge of space. The physical weight of all those air molecules pressing down on a unit of area is what we call atmospheric pressure. It isn't uniform everywhere. It changes based on the local topography, how much solar radiation or insolation an area receives, and other weather factors. At mean sea level, this weight averages out to about 1,034 grams per square centimeter.
To measure this pressure, scientists use a few different units. The standard international unit is the atmosphere, abbreviated as ATM. However, if you look at a weather report, meteorologists typically use millibars or pascals. To give you a sense of scale, 1 millibar equals the force of 1 gram pressing down on 1 square centimeter. The standard normal pressure at sea level is precisely 1,013.25 millibars.
Now, how do distinct pressure systems form? It all comes down to temperature. When a parcel of air is heated by the sun, it expands. Its volume increases, which means the air molecules spread out, causing the pressure within that parcel to drop. This creates a low-pressure cell. Conversely, when air cools, it compresses. The molecules pack tightly together, increasing the pressure and creating a high-pressure cell. The atmosphere is essentially a giant patchwork of these high and low-pressure cells interacting with one another.
The distribution of land masses and oceans plays a massive role in where these pressure cells form. Land and water heat up and cool down at different rates. During winter, continents lose heat quickly and become much cooler than the surrounding oceans, leading to the development of high-pressure centers over land. But in the summer, the situation flips. The land heats up rapidly, creating low pressure, while the relatively cooler oceans develop high pressure.
To visualize these pressure differences on a map, meteorologists use isobars. Isobars are simply lines connecting locations that have the exact same atmospheric pressure. By looking at the spacing between these lines, we can determine the pressure gradient, which is the rate at which pressure changes over a distance. If the isobars are packed closely together, it indicates a steep or strong pressure gradient, meaning pressure is changing rapidly. If they are spread far apart, the gradient is weak. When isobars form closed loops, they indicate distinct pressure centers. A low-pressure system, or cyclone, is enclosed by one or more isobars where the absolute lowest pressure is right in the middle. On the flip side, a high-pressure system, or anticyclone, has the highest pressure in the center, with pressure decreasing as you move outward.
If you ever look at a daily weather map featuring these isobars, you are looking at what geographers call an isopleth map. This was actually a question on the UPSC prelims in 1997. Isopleth maps are specifically designed to show lines connecting points of equal value, whether that's pressure with isobars, temperature with isotherms, or elevation with contour lines. So far, we've talked about pressure across the surface, but what happens as we go up? In the lower atmosphere, pressure decreases rapidly with height. Think about it. The higher you go, the less air there is above you pushing down. However, this decrease isn't perfectly constant. Because air pressure is proportional to both density and temperature, any variations in temperature or water vapor at different altitudes will cause corresponding shifts in the pressure gradient. As a general rule of thumb, atmospheric pressure drops by about 34 millibars for every 300 meters you climb. This is why mountaineers face such extreme conditions. By the time you reach the summit of Mount Everest, the air pressure is roughly 2/3 less than it is down at sea level, making it incredibly difficult to draw enough oxygen into your lungs. Here's a table illustrating this vertical variation. Notice how at sea level, we have our standard 1,013.25 millibars and a mild 15.2 degrees Celsius. But look at the 10-kilometer mark, roughly the cruising altitude of a commercial jet. The pressure has plummeted to just 265 millibars, and the temperature is a freezing -49.7 degrees Celsius.
You might be wondering, if the pressure drops so drastically as we go up, why doesn't all the air just rush upward into space? The vertical pressure gradient force is indeed much, much stronger than the horizontal one. However, it is almost perfectly balanced by an equal and opposite force, Earth's gravity, pulling the air molecules down. Because these two forces cancel each other out, we generally don't experience massive, continuous upward winds. Now, let's shift our focus to how air moves.
It's important to distinguish between wind, which is the horizontal movement of air, and currents, which refer to vertical movement. The horizontal winds we feel every day are governed by a complex interplay of several forces: the pressure gradient force, buoyant force, friction, the Coriolis force, gravity, and centripetal acceleration. Let's break these down one by one.
The primary driver of wind is the pressure gradient force. Simply put, nature hates a vacuum, and it hates imbalances. Air will naturally flow from areas of relatively high pressure to areas of relatively low pressure to balance things out. The greater the difference in pressure between these two areas, the faster the wind will blow. Initially, this force directs the wind straight across, perpendicular to the isobars.
Next is the buoyant force, which dictates whether air sinks or rises. In a low-pressure cell, the surrounding higher-pressure air pushes inward, converging and forcing the air in the center to rise. This rising air leads to unstable cyclonic weather. Conversely, in a high-pressure cell, the air is denser than its surroundings, so it sinks or subsides. As it hits the surface, it diverges outward, leading to clear, stable, anticyclonic conditions.
Rising air is absolutely essential for the formation of clouds and precipitation, but low-pressure convergence isn't the only way air rises. It can also be lifted by convection currents from localized surface heating, or a graphic uplift where wind is forced up and over a mountain range, or when different air masses collide along weather fronts. By the way, if you ever see a sudden drop in a barometer reading, it means low pressure is rapidly moving in, indicating stormy weather ahead.
As wind moves across the Earth, it doesn't have a perfectly smooth ride. The irregularities of the Earth's surface, mountains, forests, and buildings, create friction. This frictional force slows the wind down and alters its direction, causing it to cross the isobars at an angle, rather than flowing perfectly parallel to them. This effect is strongest at the surface and extends up to about 1 to 3 kilometers. Over the open ocean, where the surface is flat, friction is minimal.
Now we introduce the rotation of the Earth, which brings us to the Coriolis force. Because the Earth is spinning, winds don't travel in a straight line from high to low pressure. Instead, they get deflected. According to Farrell's law, winds in the northern hemisphere are deflected to the right of their path, and winds in the southern hemisphere are deflected to their left. This force only affects air that is already in motion, and it gets stronger as wind speed increases.
Why exactly does this deflection happen? Imagine the Earth spinning counterclockwise. The planet is wider at the equator, meaning the surface there has to spin much faster to complete a rotation in 24 hours compared to the poles. If an object, like a parcel of air or an airplane, moves away from the equator, the ground beneath it is rotating at a different speed. This difference in rotational speed creates the apparent curve in the object's path that we call the Coriolis effect.
Let's quickly bust a very common myth. You might have heard that the Coriolis effect determines which way water spirals down your sink or toilet drain, spinning one way in the northern hemisphere and the opposite in the southern. This is entirely false. The Coriolis effect is incredibly weak on small scales. The direction water drains is actually determined by the shape of the basin and the angle the water enters it, not the rotation of the Earth.
Mathematically, the magnitude of the Coriolis force depends on the velocity of the wind, the angular velocity of the Earth, and the latitude. The formula includes the sign of the latitude. Because the sine of 0 degrees is 0, the Coriolis force is absolutely 0 at the equator. As you move toward the poles, the latitude increases to 90 degrees.
The final factor is centripetal acceleration. When wind starts to curve around a pressure center due to the Coriolis effect, centripetal acceleration pulls the air inward toward the center of rotation. This inward pull balances the other forces and allows the wind to maintain a continuous, circular pattern of flow, creating the spinning vortexes we see in weather systems like cyclones. When we put all these forces together, we get distinct patterns of wind circulation. In a cyclone, which is a low-pressure system, the winds spiral inward. Due to the Coriolis deflection, they spin anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere. In an anticyclone, a high-pressure system, air flows outward, spinning clockwise in the north and anti-clockwise in the south. This brings up a fascinating question. Why don't tropical cyclones form at the equator? Remember, the Coriolis force is 0 at the equator. Without that deflection, air rushing into a low-pressure center doesn't spiral. It just flows straight in, filling the low pressure immediately and rising vertically to form standard thunderstorms. Without the spin provided by the Coriolis effect, a cyclone simply cannot organize.
To visualize this rotation in the northern hemisphere, picture a low-pressure center. The pressure gradient force pulls air straight inward from all directions, but as that air moves, the Coriolis force tugs it to the right. As all those inward rushing winds get pulled to their right, they begin to chase each other in a massive counterclockwise spiral. This is the fundamental mechanic behind every hurricane and typhoon in the northern hemisphere. Zooming out to a global scale, we can map the horizontal distribution of pressure across the Earth. By adjusting all measurements to sea level to remove the effects of altitude, we find 7 distinct global pressure belts. There is the equatorial low in the middle, flanked by matching pairs of subtropical highs, subpolar lows, and polar highs in both hemispheres. These belts aren't static. They shift north and south throughout the year as the Earth orbits the Sun, setting the stage for our global wind patterns, which we will explore next. Picking up right where we left off with atmospheric pressure, let's examine the specific pressure belts, starting at the equator. The equatorial low-pressure belt generally lies between 10 degrees north and 10 degrees south latitudes. However, it's not strictly fixed. It shifts seasonally with the apparent movement of the Sun, wandering anywhere from 5 degrees to 20 degrees north and south. This belt is incredibly important because it acts as the Intertropical Convergence Zone, or ITCZ. This is where the trade winds from the subtropical high pressure belts of both hemispheres converge. You will often hear this equatorial region referred to as the doldrums. Mariners gave it this name because of the extremely calm, sometimes stagnant air movements that could trap sailing ships for days. But why does this low pressure form? It is entirely thermally formed. Because this region lies right along the equator, it receives the highest amount of incoming solar radiation, or insolation. This intense heating warms the air, causing it to expand, become lighter, and rise, which directly creates a region of low pressure at the surface. The climate within this belt is quite unique. Because the intensely heated air is constantly rising through convection, you only really find vertical air currents here. Surface winds are almost completely absent because the air rises before it can move horizontally across the surface. As this rising air passes over the vast equatorial oceans, it picks up a massive amount of moisture. As it travels upward, it cools and condenses, forming massive cumulonimbus thunderstorm clouds. This results in heavy convectional rainfall along the margins of the belt, while the air loses all its moisture by the time it reaches the upper troposphere. Now, here is a fascinating geographic anomaly. You have intense high temperatures, and you have abundant ocean moisture, the two primary ingredients for tropical cyclones. Yet, in spite of this, cyclones simply do not form within 5 degrees north and south of the equator. Why? Because the Coriolis force, which is the rotational force needed to give storms their spin, is negligible at the equator. Without that spin, the low-pressure systems cannot organize into cyclones. Moving poleward, we encounter the subtropical high-pressure belt, which extends from near the tropics to about 35 degrees north and south. Unlike the equatorial low, which is created by heat, this belt is dynamically formed. Remember that air rising from the equator? Once it loses its moisture and reaches the upper troposphere, it becomes cold and dry. As it moves poleward, the Coriolis force deflects it, creating a blocking effect. This forces the heavy, cold, dry air to subside or sink back down to the surface at around 30 degrees latitude, creating a zone of high pressure. Because the air here is sinking, it creates anticyclonic conditions, meaning it is very calm with only feeble winds. As this air descends, it is compressed by the increasing atmospheric pressure closer to the surface, which actually heats the air up, so the air reaching the surface is both warm and extremely dry. This is exactly why most of the world's major hot deserts are located along this specific belt in both hemispheres. The descending air simply does not allow for cloud formation or rainfall. Historically, the corresponding latitudes of this subtropical high-pressure belt earned a rather grim nickname, the horse latitudes. In the early days of global trade, sailing vessels carrying cargoes of horses to the Americas would frequently get stuck in these incredibly calm, windless waters. With their ships stalled for weeks, supplies of food and water would dwindle. To save drinking water and because fodder ran out, sailors were often forced to throw their horses overboard into the sea. Hence, the name horse latitudes stuck. Let's look at how this is tested, using a question from the 2007 UPSC prelims. Statement 1 says the belts at 30 to 35 degrees north and south are known as horse latitudes. We know this is true. Statement 2 claims horse latitudes are low-pressure belts. Based on what we just discussed about subsiding air, we know they are actually high-pressure belts. Therefore, statement 2 is false, making the correct answer A, 1 only.
Continuing our journey toward the poles, we find the subpolar low-pressure belts, located between 45 degrees and 66.5 degrees in both hemispheres. Because temperatures are generally low here, these belts aren't strongly pronounced all year round and are mostly found over the oceans. Like the subtropical highs, these are dynamically produced. They form due to the Coriolis force blocking upper-level air and, crucially, the surface convergence of two major wind systems, the warm westerlies coming from the subtropics and the freezing polar easterlies coming from the poles. When they collide, the air is forced to ascend, creating low pressure.
The subpolar low exhibits distinct seasonal behavior, particularly in the northern hemisphere. During winter, the extreme temperature contrast between the freezing land masses and the relatively warmer oceans causes this belt to break into distinct low-pressure centers, specifically around the Aleutian Islands in the Pacific and between Iceland and Greenland in the Atlantic. In summer, when the temperature contrast lessens, it forms a more regular, continuous belt. Additionally, the sharp contrast between the colliding cold and warm air masses here produces the powerful polar jet streams that encircle the Earth at about 60 degrees latitude.
Finally, at the very top and bottom of the world, we have the polar high-pressure belts. These cover a relatively small area, extending from 80 to 90 degrees latitude around the poles. Their formation is quite straightforward and thermally driven. Air that rose from the subpolar lows eventually loses all its moisture. As this dry air travels through the upper troposphere toward the poles, it becomes incredibly cold. This freezing, heavy air subsides at the poles, pressing down on the surface to create a permanent high-pressure belt.
To summarize what we've seen so far, pressure systems are controlled by two main categories of factors. First are thermal factors, which are directly related to temperature. Intense heating causes air to rise, creating thermal lows, like the equatorial belt. Extreme cooling causes air to sink, creating thermal highs, like the polar belts. Second are dynamic factors. These involve the physical movement of the Earth and air, including pressure gradient forces, the seasonal shifting of the sun, and the rotation of the Earth, which generates the Coriolis force. Let's look closer at how dynamic factors work, specifically the Coriolis force. The rate at which wind is deflected by the Earth's rotation increases the further you get from the equator. In the upper troposphere, where there is very little friction, this deflection is severe. By the time poleward-moving air reaches about 25 degrees latitude, it is deflected so much that it flows almost entirely straight from west to east. This creates a massive blocking effect. The air literally piles up in the upper atmosphere, and with nowhere else to go, it is forced to subside, creating the dynamically formed high-pressure belts we see in the subtropics.
It is also crucial to remember that these pressure belts are not painted permanently onto the globe. They shift. This shifting is driven by the apparent movement of the sun. In July, during the northern hemisphere summer, the sun is directly over the Tropic of Cancer. The thermal equator, the belt of highest temperature, moves north, dragging all the global pressure belts slightly north of their annual average locations. Conversely, in January, during the northern hemisphere's winter, the sun is over the Tropic of Capricorn, and the pressure belts shift south. This shift is less pronounced in the southern hemisphere simply because it is mostly covered by water, which heats and cools more slowly than land.
Here is an assertion and reasoning question from the 2002 UPSC prelims that tests these concepts. The assertion states that 60 to 65 degree latitudes have a low pressure belt. This is true. That's our subpolar low. The reason states that low pressure areas are permanent over oceans rather than land. While it is true that oceans hold these pressures more consistently than land masses, is that the reason the belt exists at 60-65 degrees? No. As we learned, the subpolar low exists due to dynamic factors, the convergence of westerlies and polar easterlies. Therefore, both statements are true, but R is not the correct explanation for A. The answer is B.
All of these pressure belts we've discussed are the foundation for the general circulation of the atmosphere. This term simply refers to the large-scale pattern of movement of the planetary or permanent winds across the globe. This atmospheric circulation is incredibly powerful. It actually sets the surface ocean currents in motion, which in turn heavily influences the Earth's climate. This entire pattern depends on latitudinal heating, the emergence and migration of pressure belts, the layout of continents, and the Earth's rotation. This general circulation operates in three distinct massive loops of air in each hemisphere, known as cells. The first is the Hadley cell, located in the tropics.
It starts at the equatorial low-pressure belt, where convection currents force warm air to rise up to an altitude of about 14 kilometers. This air moves towards the poles in the upper atmosphere, accumulates, and sinks at about 30 degrees north and south, forming the subtropical high. At the surface, this air flows back towards the equator as the trade winds, or easterlies, completing the loop.
Moving into the middle latitudes, we find the ferrule cell. This cell is driven by the interaction of the other two cells. Here, the circulation consists of sinking cold air coming from the polar regions, interacting with the warmer air blowing poleward from the subtropical high. When these air masses meet at the surface, the warmer air is forced to rise. The surface winds in this mid-latitude cell blow from the west to the east and are therefore known as the westerlies.
Finally, at the highest latitudes, we have the polar cell. Over the freezing poles, cold, incredibly dense air subsides to the surface. It then blows outward toward the relatively warmer middle latitudes. Because of the Coriolis deflection, these surface winds blow from the east and are called the polar easterlies. Together, the Hadley, Ferrule, and polar cells act as a giant global conveyor belt. By constantly transferring heat energy from the intensely warmed lower latitudes up to the freezing higher latitudes, they maintain the general circulation of the atmosphere, which sets the stage perfectly for our next topic, the classification of these winds.
Let's dive right into the classification of winds. Winds are broadly categorized into three main types based on their scale and duration. First, we have permanent or planetary winds, which blow constantly year-round. Second, secondary or periodic winds, which change direction based on the season or time of day. And finally, local winds, which blow only during specific periods in much smaller localized areas. We will start with primary winds, also known as prevailing or planetary winds. The defining characteristic of these winds is that they blow in almost the exact same direction throughout the entire year. Because they cover massive areas of the globe, they are a fundamental part of Earth's climate system. For human activities and global climate patterns, the two most significant planetary winds are the trade winds and the westerly winds. The trade winds originate in the subtropical high-pressure areas and blow towards the equatorial low-pressure belt. This means they are strictly confined to the region between 30 degrees north and 30 degrees south. As they flow, the Earth's rotation deflects them. In the northern hemisphere, they flow as the northeastern trades, while in the southern hemisphere, they flow as the southeastern trades. When trade winds first originate in the high-pressure belts, they are descending and very stable. But as they travel towards the equator, they pick up heat and moisture from the oceans. Near the equator, the trade winds from both hemispheres crash into each other. This convergence forces the warm, humid air to rise rapidly, leading to massive cloud formation and heavy rainfall along what we call the intertropical convergence zone. An interesting characteristic of the trade winds is how they interact with ocean currents. The eastern parts of the trade wind belts are typically associated with cool ocean currents. Because the water is cool, the air above it is drier and much more stable. Conversely, by the time these winds reach the western parts of the oceans, they have warmed up and absorbed a lot of moisture, making the western regions much more humid. Next, we have the westerlies. These winds blow from the subtropical high-pressure belts towards the subpolar low-pressure belts. In the northern hemisphere, they blow from the southwest to the northeast. In the southern hemisphere, they blow from the northwest to the southeast. Unlike the steady trade winds, the westerlies are known for producing wet spells and highly variable weather conditions. The westerlies are best developed in the southern hemisphere, specifically between 40 and 65 degrees south latitudes. Because there is very little landmass to slow them down here, they become incredibly fierce. Sailors historically gave these latitudes dreaded names based on the wind's sheer volume: the roaring 40s, the furious 50s, and the shrieking 60s. Why is there such a dramatic difference between the hemispheres? The westerlies of the southern hemisphere are stronger and much more persistent due to the vast, uninterrupted expanse of ocean water. In contrast, the northern hemisphere is dominated by massive, uneven landmasses. This uneven terrain acts like a speed bump, disrupting the wind flow and making the northern westerlies much more irregular. Let's look at a past exam question about the roaring 40s. Statement 1 claims they blow uninterrupted in both hemispheres, which we know is false. They are interrupted by land in the north. Statement 2 is true, they are strong and constant. Statement 3 is true, blowing northwest to east in the south. Statement 4 is also true, as westerlies bring wet, raw weather. Therefore, the correct answer is B. Here is another question, this one from 2011. It asks why Southern Hemisphere westerlies are stronger. Statement 1 says the Southern Hemisphere has less landmass, which is absolutely correct and the primary reason for their strength. Statement 2 claims the Coriolis force is higher in the south, which is incorrect. Coriolis depends on latitude, not the hemisphere. So the correct answer is A. The final planetary winds are the polar easterlies. These are dry, bitterly cold prevailing winds that blow from the high-pressure polar areas down towards the subpolar lows. In the northern hemisphere, they blow from the northeast to the southwest, and in the southern hemisphere, they blow from the southeast to the northwest. Moving on from planetary winds, we have secondary or periodic winds. The defining feature of these winds is that they change their direction with a change in season or time of day. The most famous example of a large-scale periodic wind is the monsoon. Other examples include land and sea breezes, mountain and valley breezes, and even localized cyclones. The term monsoon refers specifically to a seasonal reversal of wind direction. Traditionally, geographers explained monsoons as essentially massive land and sea breezes, or as a giant convectional circulation system. This massive shift is primarily driven by the differential heating of continents and oceans over the course of a year, guided by the apparent movement of the sun. During summer, the sun's apparent movement shifts north, pulling the trade winds with it. An intense low-pressure core forms over the northwest Indian subcontinent. As the southern hemisphere trade winds cross the equator to fill this low pressure, the Coriolis force deflects them to the right. They approach the Asian landmass as the moisture-laden southwest monsoons. In winter, the entire system reverses. A high-pressure core develops to the north of the Indian subcontinent. This anticyclonic movement produces divergent winds that travel southwards towards the equator. These are the northeast or winter monsoons. While mostly dry, they do pick up some moisture over the Bay of Bengal, bringing important precipitation to the east coast of India. While we often associate monsoons primarily with India, they actually flow over a vast area, including Pakistan, Bangladesh, Southeast Asia, and even northern Australia. Interestingly, outside of India, in eastern Asiatic countries like China and Japan, the winter monsoon is actually stronger and more dominant than the summer monsoon. Let's look at smaller periodic winds, land and sea breezes. During the day, land heats up much faster than the ocean. The warm air over the land rises, creating a local low-pressure area. The sea remains relatively cool, maintaining higher pressure. This pressure gradient forces cool air to blow from the sea to the land, which we call a sea breeze. At night, the exact opposite happens. Land loses its heat much faster than water, so the land becomes cooler than the sea. Now, the air over the relatively warm ocean rises, creating low pressure there. The pressure gradient reverses, and cool air flows from the high-pressure land out to the sea, creating a land breeze. A similar thermal process happens in mountainous regions. During the day, the mountain slopes get intensely heated by the sun. The air just above the slopes warms up and rises. To fill the gap left by this rising air, cooler air from the valley floor is pulled upwards along the slopes. This upslope wind is known as a valley breeze. During the night, the mountain slopes cool down rapidly. The air in contact with them becomes dense and heavy, and gravity pulls this cold air down into the valley. This downslope flow is the mountain breeze. When this involves very cold, dense air draining from high ice fields or plateaus into a valley, it is specifically called a katabatic wind. Finally, we reach tertiary or local winds. These are produced by highly localized differences in temperature and pressure. Because they are driven by local geography, they are confined to small areas and only occur in the lowest levels of the troposphere. Let's explore some famous examples from around the world. Local winds are generally classified as either cold or warm. Here are some notable cold winds. The Pampero affects Argentina, while the Bora blows along the Adriatic coast. The Mistral is famous in France, and the Nor'easter brings blizzards to Canada. We also have the Tramontane in Italy and the Southerly Buster in Australia. On the other hand, we have warm local winds. The Föhn warms Switzerland, while the Chinook affects the North American prairies. The Lu brings intense heat to India, and the Sirocco blasts North Africa. The Harmattan causes dust storms in West Africa, and the Santa Ana brings dry, dusty conditions to California. Let's look closer at a few of these. The Lu is a notoriously hot and dry wind that blows across the plains of northern India and Pakistan. Originating from the deserts of Iran and Pakistan, it typically strikes in the afternoons during May and June. The Lu is brutal, with temperatures invariably soaring between 45 and 50 degrees Celsius. The foehn is a gusty, dry, hot wind found in the Alps. It develops on the leeward side of the mountains. As air is forced up the windward side, it loses its moisture as rain or snow. When it descends the leeward side, it compresses and warms rapidly. This warm wind melts winter snows, helping animal grazing, and even aids in the ripening of grapes. In North America, a similar foehn-like wind is called the Chinook. Blowing down the eastern slopes of the Rocky Mountains into the prairies, the Chinook is so warm it's known as the snow eater. It can dramatically raise temperatures by 5 degrees Celsius in just 20 minutes, which is incredibly beneficial for ranchers, as it clears winter snow from the grasslands. The Sirocco is a hot, dry, and dusty wind originating in the Sahara or Arabian deserts. It is essentially a tropical air mass that gets pulled northward by low-pressure systems moving across the Mediterranean Sea. In North Africa, its scorching heat withers vegetation and crops, and it can even reach hurricane speeds. As the Sirocco crosses the Mediterranean Sea, it absorbs water vapor, cooling down slightly. By the time it reaches southern Europe, it brings storms and wet weather. Because this wind carries massive amounts of fine red dust from the Sahara Desert, the resulting precipitation is sometimes tinted red, a phenomenon historically known as blood rain. The harmattan is another infamous wind from the Sahara, blowing southwest into the West African subregion, deeply affecting countries like Nigeria. It is so thick with dust that it actually blocks out a significant amount of solar radiation. This lack of sunlight further lowers temperatures during the colder, dry months from November to March. Shifting back to cold winds, the Mistral is a violent, freezing wind that rushes from the Alps down through the Rhône Valley in France towards the Mediterranean. Its high velocity is intensified by a funneling effect as it squeezes between the Alps and the central Massif Plateau. It is so severe that it can bring blizzards to southern France. There are several other notable cold winds. The Bora is a cold northeasterly wind along the Adriatic coast, very similar to the Mistral. The Tramontane, Levantar, and Gregale also affect the Mediterranean. Down in South America, the Pampero is a sudden burst of freezing polar air that sweeps across the pampas of Brazil, Argentina, and Uruguay. Let's test our knowledge of local winds with this 2001 exam question. We need to match the wind to the region. We know the foehn is in the Alps, so A matches with 4. The Santa Ana is in California, so C matches with 3. The Zonda is in Argentina, so D matches with 1. Even if we don't know Sarmoun, elimination leaves us with option B as the only correct answer. This global map beautifully summarizes the complex network of local winds we've discussed. You can see how geography dictates these patterns, from the hot Chinooks and Zondas descending mountain ranges, to the dusty Sirocco and Harmattan blowing out of the Sahara, to the freezing Mistral and Bora funneling into the Mediterranean. To wrap up our discussion on the classification of winds, remember that winds operate on 3 distinct scales. Primary planetary winds drive the macro-global climate. Secondary periodic winds, like the mighty monsoons, dictate seasonal weather patterns. And finally, local winds, though confined to small areas, have profound impacts on regional agriculture, weather, and daily life.